Yay, thank you. So like I was telling you earlier this period, all spheres roll down ramps at the same rate. So I'm going to demonstrate that for you now. Here I got a wooden sphere with a gigantic radius, but it's not that dense. Here I've got a steel sphere with a much smaller radius, but actually a very different mass as well. But it turns out that all spheres roll down ramps at the same rate. So these two spheres, if they were to have a race, who's supposed to win? Neither of them, exactly. Please watch in wonderment as I race these spheres down the track, and neither of them ends up winning. Here we go. Here's the big sphere, small sphere. 1, 2, wait, stop that. Okay. 1, 2, 3, wait.
Science is a lie.
It totally is. It really is. Anyone who tells you otherwise is lying. Okay, here we go. Whoa.
So, Mr. Shana, do you want to tell us why that happened?
Well, I can't tell you why. Last period, believe it or not, the metal sphere won the race every time. Now the wooden sphere wins. It's just, I guess there's some element of randomness happening here. Really, it's like, it just depends on who gets started quicker. It's kind of weird, you know? Okay, here we go. Wait,
that's because it's cheating.
Why is that stupid thing always win? It's cheating now.
Yeah, he swerved over into the other lane.
Tell me, does this guy have more or less inertia than a normal sphere?
More. A lot.
Well, look at how it's shaped. Doesn't it look like it used to be a sphere, but then they shaved away some of the sphere to make it look cool? So maybe this guy has slightly less rotational inertia than a true sphere. So let me race a couple of true spheres down this ramp. How about a marble? Here, we'll do a steel ball and a marble. Now, for sure, they'll totally tie, because science is totally not a lie. Here we go. Am I square?
Woo!
Wow, now the sphere wins. I mean, the steel sphere wins. This guy had some trouble getting started. Let's try a different. Another sphere. Oh, here we go. This is the last one I'm going to do. These two are totally going to tie now, unlike any of the other spheres. Okay, here we go. All right. Stop that. Okay, here we go. Woo! Well, there's obviously some differences there because they're supposed to tie. They're pretty close, but friction must be an issue. Who gets started quicker is an issue. Well, anyway, that's the end of that tune. Let me get this out of the way. Alrighty, am I running over the cord? Thank you. And then let me get this out of the way. I'm not thinking very well. I should tell posterity. I think I'll tell everyone. Last night I had a gallbladder attack. So if you're watching this on video, you're watching a teacher had a gallbladder attack last night, and it was not good. And I'm not very comfortable right now. I need a lot of discomfort. But it's not going to kill me, and that's good. Like having intense pain knowing it's not going to kill you is very different from having intense pain knowing it's not going to. Okay, great. Here we go. Next thing we're going to talk about, the vector nature of angular momentum. Conservation of angular momentum. Suppose I have a human being, and this human being is standing on a turntable, and the human being has in his hands a wheel that's rotating like this, okay? And this is the front of the wheel, so how am I going to make that the front of the wheel? I'll do this. Okay, so here's my human being. And this person is grasping this with his hand and that with his hand. Okay, so are you seeing that the wheel is rotating, the front of the wheel is rotating towards the person? So like, if I can do that here, it'll be like the person, like the wheel's rotating like this, and the person's holding it like this, and they're standing on this turntable. Okay? So let me ask you this question. What's the direction of the angular momentum of that wheel right now? Remember to do right hand rule. What's the direction of the angular momentum? Good, well no, because it's got to be the direction that your thumb points.
That way.
So yeah, it's going clockwise, but what's the direction that my thumb points?
To the left.
Yeah, to the left. Exactly. So I want you to see that right now, this angular momentum is pointing to the left. And now, let's suppose that the person who's holding the wheel decides to rotate it this way, horizontally, while they're standing on the turntable. So it was rotating like this, then they turn it like this. So now it used to be going towards them. Now looking down on it, it's going counterclockwise.
I got confused.
So the person has now turned it, and it's rotating it counterclockwise. And so this person's, I guess, grasping one of these with one hand and grasping the other with the other hand. I don't know. And then they're standing on a turntable. Okay. Well, tell me, now, what's the direction of the angular momentum of the wheel?
Up.
Thank you very much, Imani. Up, correct? Because right hand rule, my fingers curl in the direction of rotation, my thumb points in the direction of the angular momentum. So that angular momentum, which I'll call L1, is pointing upward, okay? Well, are there any external torques happening? Is someone standing next to this guy making things rotate faster or slower?
No.
No, there's no external torques. So we would expect angular momentum to be conserved, but angular momentum is a vector quantity, which means the initial angular momentum in the x direction has to equal the final angular momentum in the x direction. And the initial angular momentum in the y direction has to equal the final angular momentum in the y direction. But you tell me, initially, with the wheel just rotating this way vertically, what's the angular momentum in the y direction? According to this drawing. Is there any angular momentum in the y direction, according to the drawing? No. I've got angular momentum, but it's in the x direction. So I want you to see that when the tire is rotating this way, there's no angular momentum in the y direction. There's just angular momentum in the x direction. So the initial angular momentum of the system in the y direction is equal to 0. So here comes my next question. Now, I've just turned the wheel so that the angular momentum of the wheel is pointing upward. So I've got some positive angular momentum. What's going to happen to the dude standing on the turntable? Well, let me tell you, the angular momentum on the right side of the equation, what's it going to have to end up equaling? 0, right? So I need somehow to get a downward angular momentum. I've got an upward angular momentum due to the rotation of the wheel. How am I going to get a downward angular momentum? Remember, I got a guy standing on a turntable.
He's going to turn clockwise?
Yeah, thank you very much, Imani, and that's what you were motioning, Sean. This dude is going to have to turn clockwise, right? I'm going to need an angular momentum going in the opposite direction, right? So that the sum of the angular momentum of the wheel and the dude, or the girl, are equal to 0. Now, the angular momentum of the wheel is what it is, but the angular momentum of the person on the turntable, let's say I as a teacher, I want to accentuate the effect of turning the wheel. That is, I want the person who's grasping the wheel in their hands, I want them to turn it and have them spin really, really fast. I want them to have as big an omega as possible. So tell me, what kind of human being should I choose to be the one holding the wheel?
Lily.
Let me get someone else, someone who didn't have me last year. What kind of person do I want to choose to hold the wheel if I want omega to be as big as possible?
A little person.
Yeah, a little person. I want to choose someone really thin, right? Someone who has all their mass concentrated at the axis of rotation so that they have a very small rotational inertia. Because small rotational inertia means big omega. You guys okay with that? So who's going to volunteer? Who's going to do this? Imani? Okay, Imani.
You guys are wimps.
They are windy wimps. Okay, let's bring this out a little so you don't bang into the wall. Okay, go ahead and climb aboard. Alrighty. And now, here, just a second. Grasp the wheel. Okay. Now, your right hand, go ahead and put it under the wheel. Yeah, just so it's easier for you to rotate it. Go ahead and rotate it that way. Good. Great. Now rotate it back. And can you rotate it the other way easily? Maybe you need your hand on, I don't know, hold it however you're comfortable.
Like that?
Yeah, no, but I mean, go ahead. Yeah, just like that is good because you'll be able to go this way or that way. Okay, here we go. First step, I need her to have this type of angular momentum for the wheel. So I'm going to, okay, now go ahead and rotate it. Look at that. And do you notice, go ahead and go back to vertical and go the other way. You guys okay with that? And do you see, what's the relationship between the way that the wheel is rotating and the way that Imani is rotating? Like if Imani is going and looking down on her, she's, okay, right now Imani's going clockwise. What way is the wheel going looking down on the wheel? Yeah, counterclockwise, right? Because those two angular momentums have to be equal and opposite. Alrighty. Here, let's, here, I'll take that. Thanks a lot, Imani. Give Imani a hand. Alrighty. Do we have any other volunteers?
It's fun.
It's very fun. Okay, come on up. Yay.
Yeah, the jacket comes off.
Yeah, we got to shed some of that rotational inertia. Okay, go ahead and climb aboard. Hey, okay. All right. And go ahead and practice doing it horizontal. Good, because yeah, you don't want it to hit your body, and you're doing a nice job of not having it hit your body. Here we go. Okay, let her rip.
Go.
Oh my gosh.
Yeah, it's a really cool effect.
Whoa.
Don't fall off. That would be bad. Yeah, it's really cool, and you can feel it too. You can feel when you're rotating it that it's kind of resisting a little, and then you end up rotating.
Wow, physics is cool.
Cool. Okay, you good?
Love this class.
Now you're dizzy. Alrighty, so that's it. Conservation of angular momentum. Now, let me stop with this. Now, here's another question. What about the x component of angular momentum? Where did it go? Because there's no x component of angular momentum now. Where did that x component of angular momentum go? Who gained the x component of angular momentum? Or what gained it? What's gonna have an additional rotation like this? It's not the dude, he's not rotating like this. It's not the turntable, it's not rotating like this. What's that? No, the wheel's rotating like this. It's got no component of rotation like this. tell me, what's the person and the turntable, what are they attached to? What's that? Yeah, the Earth. Yes, the Earth just acquired a little bit of angular momentum.
Oh.
Of course, it's unmeasurable because the Earth is really, really big. But yeah, that's where that angular momentum went. You know, when she turned the wheel like this guy went away, and now the Earth is rotating just a little bit faster. Okay, that way. All right. Hey, there's another demo I need to show you, and it pertains to impulse momentum. Impulse momentum, force times change in time equals change in momentum. Well, we have a rotational version, torque times change in time equals change of angular momentum, and those are vectors. And so this equation here explains the precession of tops. Like, have you ever noticed if you do a top and before the top falls over, it kind of spins, it's kind of tilted, and it's spinning round and round at that tilt before it finally falls? Well, I want to show you why that happens. So here's the first thing, okay? I'm holding this wheel. I'll hold it by one hand. And let's say I want to let the wheel drop. So I just do that and I let the wheel drop. It goes from the wheel being vertical to the wheel being horizontal. No big deal, okay? But I want you to notice something that happens when I give this wheel a lot of angular momentum. Now I'm going to drop it as before and watch what the wheel does. Do you see that? Like I tried to, I'm not going to manhandle it, I want to do it really gently. I try to drop it, and what does it do? Do you see how it's rotating to the right? It's precessing to the right. I drop it, it goes to the right. And what will happen, let's say I rotate the wheel in the opposite direction. Now if I drop it, what's going to happen?
To the left.
Yeah, it's going to go to the left now. Okay? And I need to show you why that happens. Why is it that when I'm rotating this guy like this, and then I drop it, it goes to the left? Okay? Here. Oops. So, let me think. Yeah. So, I got this wheel, alrighty, and think, how was I holding it? Wait, oh no, I was holding it. Yeah. I'll go like this. Alrighty, so you're okay that I'm holding the wheel like that. And then I'm going to let the wheel fall. But before I let the wheel fall, let me ask you this question. What's the direction of the angular momentum of the wheel right now? Using right hand rule. Thank you very much, Earl. You guys okay that it's to the left? Because the wheel's rotating this way, so my angular momentum is to the left. But I'm going to now let it fall. And what I'm doing is I'm letting it rotate about this point, right? I'm rotating about this point. But the rotation is this way, okay? And so if I were to do right-hand rule on that rotation, the rotation that's moving the wheel down, I hope you see that I'm giving a torque that's coming out of the board. That is, my torque is going to be in that direction because I'm letting the wheel fall, okay? So the torque's coming out of the board. If I looked at it from above, so imagine, here's my eye, and I'm looking at it from above. So now here's the top of the guy's head, and here's the handle, and then here's the wheel. Okay, and then here's the other handle. Let's say, although maybe I should make it bigger so it matches that. Here, just a second. Here's the guy's head, then here's the handle, here's the wheel, and then here's the handle, Okay. I'm letting the wheel fall. Now the wheel is still rotating, so the moment of inertia, I mean the angular momentum is coming out like this, but I'm letting the wheel fall, which means if I'm looking down on it, my torque is in this direction. Now torque is a vector, that vector can go anywhere. And you see that the direction of the torque is going to be the same as the direction of the change in angular momentum. So because my torque is down, and I can put that vector anywhere, that means my change in angular momentum is going to be down. I'm sorry, to the left. Since my torque is to the left, the change in angular momentum is going to be to the left. Which means this wheel isn't going to fall down. This wheel is going to turn to the left. This is going to be the new angular momentum. It's going to turn to the left because of that change in angular momentum. Here, let me show you visually, okay? I'm holding it like this, and the wheel is turning like this. And then when I let it down, I'm exerting a torque that way, which makes a change in angular momentum that way, which means my wheel is going to want to turn this way. I want it to go down, but the wheel's going to turn that way. So let me show you what I'm talking about. Okay, so I drop it, and it goes down. You see that? Does anyone want to hold this in their hand and try it? Okay, come on up, Paul. Paul was first. Okay, come on up, Charlotte. I just want you to feel it and, you know, be relaxed in it. Don't try to manhandle it. Okay, here, I'm gonna get it rotating really fast.
With 2 hands?
Yeah, 2 hands for now, but then you're gonna transfer them both to one handle. Okay, transfer them both to one handle. Okay, and now just let it drop. And do you see how it naturally wants to turn? You see? That's also one of the reasons why on a bicycle, it's very hard to fall down off of a bicycle. You know, if you start falling down, you end up just turning. You don't fall down just yet. So you can feel that, right?
Yeah.
Okay, good. Thanks a lot. And whoever wants to play with it after class, be my guest. So let me show you a very famous demo of this concept. Here, just a second. Oh wait, I'll do it farther out. Of course, it's all on video. All righty. Great. So, for example, you know, I'm going to hold this like this, correct? I'm going to hold it like this, and if I let it go, you know, it's just going to fall like that, right? But what if I started rotating in a rotation? Okay, just a second. So now I'm holding it. And you see how it doesn't want to fall. All it wants to do is turn. Because the torque is changing its momentum, and it's just making it turn instead of fall. Now eventually, as this guy slows down, it'll go horizontal. But when it was going really fast, it's going to stay you know, vertical, or try to stay vertical. You guys okay with that? So here, I'll do it one more time.
How cool.
Yeah. It just turns instead of falling. All right. So, you know, I just wanted to give you these demonstrations really to show you the vector nature of angular momentum. The fact that, you know, you want it to drop down, but it just ends up oh wait, where is that? No, you want it to drop down, but it just ends up precessing, you know? Or the vector nature, you change the rotation of that wheel, and you start rotating. All right, hey, any questions or issues? And hey, we're done, bye-bye.